In this class, we will discuss the Runge-Kutta method. Here we will consider both second order as well as fourth order Runge-Kutta method. So first we will discuss about the second order Runge-Kutta method. So this method also we will use to solve ordinary differential equation numerically. So let us consider this differential equation y dash is equal to dy by dx, which is f of x comma y with initial condition y of x0, which is equal to y0. This is same as that of Euler's method that we discussed in the last class. And we have to evaluate the value of y at xn equal to x0 plus nh. How this x0 plus nh come? That's all we discussed in the Euler's method. So first value, if you consider x0, then to reach x1, we have to add plus h with this x0 first value. Then we'll get the second x value, so that this h is the step size, okay, or the interval. So this is the method, and in general, if you consider, if you add the second, if you want to get the second point, then you have to add 2h, then it will become x2, x0 plus 3h, then it will become x3, and so on. So in this, we are considering the function is varying like this. So this is your x values, and your function is something like this, and the starting point of this function is at x0. Okay, and if you want to get the next x value, for example, for better view, I will consider x1 here. So this is x1, and then you have x2 and x3 somewhere here, and so on. So to get this x1, you have to add a step of h with this x0. Okay, so if you want to get the xn, that is the final point, so that will be somewhere here. So that xn will be at this point, and that xn, if you continue this process, then that will be x0 plus nh. This will be equal to xn. So this we already discussed in the Euler's method. So this is your y. Okay, this y is nothing but f of x comma y. This is f of x comma y, and this f of x comma y is nothing but your dy by dx. So you have given a differential equation which is dy by dx equal to something. Okay, that function, that dy by dx is varying like this. That f of x or f of x comma y, that is varying like this. So if you want to go for the next x value, you have to add a period or the step size of h with the previous or current x0 x value. Okay, so that is this step. So if you want to get xn, value of xn, you have to add x0 with nh, where n is 1, 2, 3, 4, etc. So if you want to get the second point, for example, if you want to get x1, then this will be equal to x1 will be equal to x0 plus n will become 1, so that is 1h, and so on. You can calculate all the other x values. So now if you are integrating this this particular equation that is given, dy by dx equal to f of x comma y, that is our function. So if you are integrating that particular equation, then we will be getting equation like this. It will be y1 equal to y0 plus x0 integral x0 to x1 f of x comma y dx. Okay, so that is the result of the integration if you are doing the integral for that particular equation. Okay, now we'll move to the next step. So you can see integrating that particular equation, that will give you this y1 equal to y0 plus integral x0 to x1 f of x comma y dx. Now assuming that f of x comma y, that is a function which is equal to f of x0 y0 plus f of x1 y1 by 2. Okay, so in this case we are having some assumption. In Euler's method we had the assumption that is given in this bracket. If you have if you haven't any idea about this, you just please visit the previous video for Euler's method. And in Euler's method we have this particular assumption that we considered. For example, if you are considering that dy by dx variation with the x, that is our function f of x comma y, that is dy by dx. And this, if you are considering that is varying from x0 to x1, for example. So we are just considering the first 2 points. So this is at x0 and this is at x1. So I know what is the value at x0 for this y. So this is my y0. So this will be given by this initial condition y of x0 equal to y0. That will be given. So if you know only this initial condition, then only you can solve this equation, differential equation, by using Euler's method as well as the Runge-Kutta method. Okay. So this initial condition is given so that I know what is the y value at x0, that is the y value at the initial x value. Then what will be my y value at the second x value, that is x1, at x1. What will be that y value? That we have to find out. Okay, so in the Euler's method, we have assumed that in between these two intervals, in between these 2 points, in between these 2 points, x0, y0, and let's say this is y1. So this is x1, y1 point. So in between this x0, y0, and x1, y1 point, the function remains constant. We have made some assumption like that, so that our f of x x1 comma y1 is equivalent to f of x0 comma y0. This is this assumption we have made for this Euler's method, and we consider that this function is constant in that interval x0 to x1. So that we have taken this f of x0 comma y0 outside, and we got the result like y1 equal to y0 plus uh, f of x0 comma y0 times, then that integral will come with the dx, so that it is varying from x0 to x1. So this range x0 to x1, this we call it as h, so that integral x0 to x1 dx will become h. Okay, so that we will get y1 equal to y0 plus h into f of x0 comma y0, that is y1. So this is the assumption that we made for the Euler's method, that within that interval, very small interval of h, the function is constant. Okay, so this is only possible when you are considering that interval very small. Okay, otherwise that assumption is wrong. So this was the method for Euler's, okay, assumption that we made for Euler's. But in case of Runge-Kutta method, we are considering assumption like this. We are considering f of x0 comma y0 plus f of x1 comma y1 by 2 as f of x comma y. So we are considering the function in between these 2 points. The function is somewhere here, f of x comma y. So we are considering it like this. Okay, so if you are taking that particular step, so what is the assumption? Assumption is f of x comma y, that is given at a given point, that is equal to f of x0 plus y0, sorry, f of x0 comma y0 plus f of x1 comma y1 by 2. So we are considering some average of these 2 points. So what is f of x0, y0? That we know. F of x0 we know, y0 we know, so that we can calculate f of x0 comma y0. Then we want to know what is x1 and y1. So if you consider the change in this x values as within that step, if you consider it as h, then x1 will be x0 plus h, right? Then what is y1? Y1 we don't know, so that we will take that y1 assumption from this Euler's method, so that we'll get y1 as y0 plus h into f of x0 comma y0. So we'll take this as y1 and divided by 2, taking average of that. That will give you this f of x comma y. So that is the assumption that we made, or we have to make in the case of a Runge-Kutta method. So that you can see from here in this equation. Okay, so we are considering the function as in between these two adjacent points, f of x0 comma y0 plus f of x1 comma y1 by 2, as like this. Okay, we are just considering we are assuming the function is like this, so that we are taking the average of those 2 points, values of function at that those 2 points. So this is just for the case of the function in between x0 y0 and x1 y1. But if you consider any other points, you have to take the function like that. Okay, any other points also. So for just for simplification, I'm just considering these initial 2 points. Okay, so now if you consider and if you consider the integration of that function, okay, then you can say, yeah, I will explain here itself. So you can see now y1 will be equal to y0 plus h into f of x0 comma y0 plus f of x0 plus h comma y0 plus h into f of x0 plus so x0 comma y0 by 2. Okay, so you just have to substitute this particular function in that Euler's equation, then you can directly get this result. Y1 will be equal to y0 plus h into f of x comma y. Okay, so if you are considering that integration, you can see here, if you consider this integration, so this will become y1 equal to y0 plus integral x0 to x1 f of x comma y dx. Substitute this f of x comma y value in this equation, then you will get this result. Okay, in that case also you have to just consider this this term in this bracket. You can see that as a constant. Okay, then just to consider integral x0 to x1 dx as h, and then you'll get this result. So this is the result or the equation that you have to use in the case of Runge-Kutta method. And if you are substituting k1 equal to h in f of x0 comma y0, so you just substitute k1 for this x0 f of x0 into y0 times h, and then k2 if you consider f of x0 plus h comma y0 plus h into f of x0 comma y0. So if you are considering this term as your I think this is x0, yeah, this is h times f of x0 plus h, and if you consider this term as your this term you can consider it as k1 h into f of x0 comma y0, and y0 plus k1 it will come. So that term you consider this entire term as k2. Okay, so this part is k1 because you have considered h into f of x0, h into f of x0 comma y0 as your k1. So this you can replace with k1. So here we'll be getting y0 plus k1, that is this term, and then for x we are having 0 plus h that we have written here. So f of that, okay, so f of x0 plus h y0 comma y0 plus k1 times h outside h. So if you take that as k2, then you can simply write your y1 equal to y0 plus 1 by 2 times k1 plus k2. Okay, just assuming k1 equal to h of h and f of x0 comma y0, K2 is equal to h into f of x0 plus h comma y0 plus k1. So you'll be getting y1 equal to y0 plus half into k1 plus k2. So in general, so this is the next y1. If you know what is y0, what is y1, next point. So you know what is x0 and y0 from that initial condition. So what will be if I am going x1, what will be my y1? That we have to calculate. So in order to get this y1, you have to use this equation with that second order from Runge-Kutta method. So this is the method, and if you consider in general, if you consider for any point, then you can use this equation. Yn plus 1 will be equal to yn, if you know the previous value, that has to be added with half k1 plus k2. Okay, so this is the general equation for the second order Runge-Kutta method. So what actually we are looking in this method? So for example, if you consider that graph again, so we are having dy by dx in y-axis, dy by dx, or this is nothing but your f of x comma y, and this is your x. Okay, so what actually you are calculating, you know what is x0 and y0, that is the initial points. Okay, then k1, what is k1? K1 is nothing but h into f of x0 comma y0. What is this f of x0 comma y0? This is the slope at x0 comma y0, that is dy by dx at x0 comma y0. So this is nothing but dy by dx at that point, x equal to x0 and y equal to y0. I'm just writing it like this. Okay, so if what is this h? This h is nothing but dx, change in x. So these two, if you are getting cancelled, these two get cancelled, then you will get dy is nothing but k1. Okay, that is the change in the y, change in y. Okay, if you know what is the value of x0 and y0. So that is nothing but k1, right? So that is so if you are considering the slope at this point k0 y0, so you can just consider that. What is the, so if you consider the slope at that point x0 y0, that is multiplied with h will give you the value of k1. So you'll be having some k1 like this, that is the this slope. Okay, so slope multiplied with the h. So suppose I will take the h value up to this. Okay, let's say this is your x0, this is x0, and this is x1. So h, this is the h difference, h. So we are having a slope like this at this point, and if you multiply that with this h, then you will get the next y value. So what actually you are calculating, you are having this initial point over here, and you know what is dy by dx of at that point. And if so, that will give you, this is your first y value, that is nothing but y0. So this is also your y0, and from that y0, how much is the height for the next y value? Okay, so this is your y1. Okay, so that will be given by this slope, that is nothing but dy by dx, or f of x0 comma y0, multiplied with this h. Okay, so this y1, you are getting this y1 with that uh, uh, sorry, this one you will be getting k1. So this is your k1, not y1. Should have. So what is that meaning? So what's that means? For example, if you consider Euler's method, you are having this particular equation. So in this equation, you can see what is y1 and y0. So from this equation, Euler's method, you can see this is your x, this is your y, or this is also your f of x comma y, and this is also your dy by dx. So if you consider, if you know what is y0, for example, this is your x0, and let's say this is your x0, and this one is your x1. I'm taking only the nearest 2 points. And let's say this is your y0. So at x0, you're having this much of y. So this is your first point, that is initial condition. And so if you are considering this equation, what this equation implies, so this equation is nothing but, so if you know dy by dx at x0 and y0, dy by dx at x equal to x0, y equal to y0, that is this one, f of x0 comma y0. So if you multiply that with h, what will happen? So this h is nothing but change in x. So this is nothing but dx. So this h and this dx can get cancelled. So that we will be getting dy. So what is dy? What is change in y? So this y is, in this case, for example, if you consider the next y value as y1, for example, this is your y1 and this is at x1. So what is the change from this y0 to y1? That will be your dy. That is nothing but y1 minus y0. So if you get this part, these two part, then we'll be directly getting that y1 will be equal to y0 plus dy by dx at x equal to x0 and y equal to y0. That is nothing but f of x0 comma y0 times h. Okay, that is the Euler's equation. So if you know what is the slope at this point, for example, so if you know what is the slope at this point, let's say this is your slope, okay, and that is multiplied with h, value of h, and add with that with your y0. If you know y0, what is the slope of that point at y0, x0, y0? If you know that, multiply that with h and add with the y0 value, then you will get the second point y1. That is the meaning of the Euler's equation. Okay, so that you'll be getting the second y value. So your slope, let's say your slope is something like this, and you're adding with y0 and you'll be getting this value. Okay, but in the case of Runge-Kutta method, this slope is slope that is multiplied with h, that will give you k1. Okay, and you also have another slope which is k2, and that slope, if you check that equation, you can see that the second slope will be somewhere here at y1, sorry, the present x1. Okay, so this is, let's say this is your second slope. Okay, and that is k2. So what is k2? You can see here, k2 is this quantity at x0 plus h, y0 plus k1. What is my k2? Sorry, what is my slope? So that is f of x0 plus h, f of x0 plus h, comma y0 plus k1. Okay, f of x0 plus h, y0 plus k1. So at this point, what is slope? So that will be, given by k2. And if you consider these two values, k1 and k2, and calculate if you know this slope, and you have to project that slope into here, like this, like something like this, and then extend that, and where it is meeting on this value after at x1, so that will be your y1. Okay, that is the meaning of the equation y1 equal to y0 plus half k1 plus k2. So this is how we will calculate the value of y with each of these uh, values given. Okay, the initial conditions given. Okay, so this is the second order Runge-Kutta method, and in the case of fourth order Runge-Kutta method, so in the case of fourth order Runge-Kutta method, we have to consider uh, this equation I will write it here, yi plus 1 will be equal to, I will write it below, so yi plus 1 will be equal to yi plus 1 by 6 of k1 plus k2 plus k3. So this is 2k2 plus 2k3 plus k4. So this is equation for the fourth order Runge-Kutta method to solve the differential equation numerically. So in that case, we will be having 4 different slopes. So that will give you much more accurate result. So in this case, what we are doing, in the first case, for the case of Euler's method, we are considering only one slope, f of x0 comma y0. Okay, multiply that with h and add that term with y0, you will get the next y value. But in the second order Runge-Kutta method, we are considering two slopes, k1 and k2 we are considering, and we are evaluating the value of y1 as an average with an average of that k1 and k2. So we'll get the k1, sorry, y1, which will be much more accurate. But in the case of fourth order Runge-Kutta method, we will be considering 4 such slopes, and so that we will be getting much more accurate result. Okay, so just consider that. So let us consider this as your k1. Okay, you know this is k1, and the next value you have to consider is at as you can see from here, what is this k1, k2, k3, all those values which are given here. For fourth order case, k1 is h into f of xi comma yi. This is a general equation for ith y value. Sorry, I1, I plus 1th y value, if you know what is the ith I value. Okay, or you can consider n plus 1, you can consider it as a y equal to n, yn plus 1 equal to yn plus 1 by 6 and so on. That is also possible. So if you know yn, then you have to find out what is a yn plus 1. Okay, so this is k1, equation for k1. So this k1 is h times, right, again k1 equal to h times f of xi comma yi, the known points. If you know the slope, multiply that with h, you will get k1, similar to that of the previous example with the second order Runge-Kutta method. And if you consider k2 will be equal to f of the xi plus h by 2 comma yi plus h by 2 times k1. This is the equation for the k2, and k3 will be equal to f of xi, that is known point, plus h by 2 comma yi plus h by 2 k2, and k4 will be equal to f of xi plus h comma yi plus h into k3. So I'm not going to discuss the theoretical derivation of all this in here, but I will just show you how it is. It can be uh, represented as graphically. Okay, so we are only focused on the numerical calculations based on this method. Okay, so in this figure you can consider K1 first, as we discussed earlier, and then we have the second uh, value K2. And where is K2? You can see from here. We are considering the slope for this K2. We are considering the slope at xi plus h by 2, xi plus h by 2, and so xi plus h by 2, where it will come. So if you are considering x0 and y0, x0 is your xi now. Okay, this is your xi, and I have to find out what is, I know what is yi also. So this is your yi now, and I have to find out what is the yi plus 1, right? Yi plus 1 at xi plus 1. So this is my xi plus 1. Okay. So now if you consider the other values, K2, all the values K1, K1 we know, we already discussed about K1, how it will be coming, the slope K1, and then that is nothing but the slope at x0, y0, or the initial point, or the point that we know, that is multiplied with h, that is K1. Okay. Now what will be K2? K2, for K2 also we have to consider the slope, and that slope is nothing but f of xi plus h by 2, and yi comma yi plus h by 2 times k1. Okay, so in that case we have to consider the points where we have to find out the slope first. So the slope has to be calculated at the point xi plus h by 2. So xi plus h by 2 is the midpoint of this, in between this xi and xi plus 1. So this is your xi plus h by 2. Okay, so the middle of that, and then we have yi plus h by 2 times k1. So this is hk1, this slope that will be giving you hk1, and half of that. Okay, so half of that, so that is plus yi. So that is nothing but this quantity. So this entire quantity is yi plus h by 2 k1. So that is h by 2 we have to consider. So it will be the middle of this one. So the slope will be this one. So this term, this particular term will be giving you h by 2 times k1. Okay. So that is with yi. Right. So this point. So y0 is this one. This is, so yi, you can consider it as yi. So yi plus h2, h by 2 k1. That is this term. Okay. So this term. So we have to, basically we have to find out what is the slope at that point where these two lines intersect. So that slope, for example, it is something like this, and that is represented as K2. Then project this slope with the h distance. So it will be reaching somewhere here. So this, again, you have to move up to, this is xi plus h by 2. So we have to consider xi plus 3h by 2, right? For the next x value. So here we are having xi plus 1, that will be xi plus h, right? So that is, then we have to go for this 3h by 2, so that it will be, this one is nothing but xi plus 0.5h, this is xi plus 1.5h. Okay, So up to that point, we have to project this. So this is at this point, okay, and you consider this. So this is your K2, right? This is your K2. If you are considering the slope as K2, then this quantity will be H times K2, and if you take half of that, it will be something like this. Okay, so that much of quantity we have to consider at this point, at the midpoint. You can see this theory, you may get some little confused, but you can look for some other sources. So this HK2 by 2 quantity that you have to consider here, this will give you K3, right? Because you have to consider Xi plus H by 2 for K3 also. You can see for K3 also, you have to consider the X value as Xi plus H by 2. So we have to consider the same point for X, and Y, for Y we have to consider Yi plus H by 2 K2. So what is H by 2 K2? H by 2 K2 is this quantity, this much of quantity. So only this much you have to consider for Y. So from where we have to add that Yi, from Yi we have to add H by 2 K2. So that H by 2 K2 I am adding here. So we have to consider what is the slope of that at this point. What is the slope of the function at this point? That will be given by the value K3. So this is your K3. Okay. Now further, if you consider, okay, each time you have to multiply this. I think I missed one H here. So we have H in all these terms. Sorry about that. This is H times. I had to multiply H times all those terms. So for K3, you'll be having slope like this. And now you have to extend that slope. This K3 slope you have to extend again. So that again it will reach somewhere here. Something like this. And you will be getting this quantity. And this is nothing but your HK3. H times K3. And this much shift you need for the Y value from Yi for the K4, Yi plus HK3. And Xi, what is X value? Xi plus H. So the final K4 will be at this point. Okay. So from Y0, it has to move with this much of quantity, HK3. So let's say that is about this much. Okay. So we'll use some other color for K4. So it is, let's say this is up to this quantity you have to move. So that is nothing but this HK3. Okay, HK3 we have to take. In that case, we have to take the entire quantity. We don't have to take by 2 here because we are having HK3 for this case. So this is your HK3. And you have to find out what is the slope at this point. This point. So you'll be getting K4 somewhere here. K4. This is your K4. Okay, and you add all this quantity and take average of that. In the second order Runge-Kutta method, we took the average 1 by 2 times K1 plus K2, but here we can take the weighted average, and the weighted average for this case, the uh, weighted average for this all these K1, K2, K3, K4 values, if you consider, then it is 1 by 6 times K1 plus 2, K2 plus 2, K3 plus K4. Okay, this is the most used average value, weighted average value. Okay, that's why we are considering that one. And this is this has to be added with the known value Yi, then you will be getting the next Yi. next y value. So this is most accurate because we have to consider all these points, and we have to consider these two midpoints, okay, k1 and k2, sorry, k2 and k3 for this mid value, xi plus h by 2, and we have two slopes at the endpoints at x0 or xi at xi and xi plus 1 or xi plus h, if you consider it as xi plus h like this. Okay, so we are considering slope at this point, slope at the initial point, and slope at the midpoint, and taking the weighted average of all those things and adding it to this y, so that it will be much more accurate. Okay, so this is just the theoretical part, but we don't have to look much into that. We just need these equations to solve the differential equation numerically. So we have to consider these equations for fourth order fourth order Runge-Kutta method, and this equation we have to consider for the second order Runge-Kutta method. And we will just consider one example for the second order case. In the same way, you can do one example for the fourth order case, and you can see. After this, we'll explain the program for this Runge-Kutta method also. So here we have the question: find y of 0.2 for the case of y dash equal to x plus y square. So this is the given differential equation, dy by dx equal to x plus y square. Okay, and we had to find out what is the value of y at 0.2. So solution of this differential equation at 0.2, that we had to find out. And given the initial condition y of 0 is equal to 1 with step size or step length of 0.1 using second order Runge-Kutta differential method, Runge-Kutta numerical method. So that we have to find out. So this is these are the given quantities: dy by dx equal to x plus y square, y of 0 is equal to 1, that is the initial condition, and h is equal to 0.1. So in this case, if you use second order second order Runge-Kutta method, then we will be getting k1. First, we have to use it. What is k1? K1 is nothing but h into f of x0 comma y0. Okay, so you substitute x0 and y0 here. What is x0? X0 will be equal to 0. That is initial condition. This is your x0 value. Y of whatever it is in the bracket, that is your x0. So x0 is 0. Y0 is nothing but your y0. Y0 will be equal to 1. So you substitute these two value in the given differential equation, that is y dash is equal to x plus y square. So if you substitute x equal to 0, this term will become 0 and y will become 1. So this is 1. So y dash is equal to 1. So this is 0.1 is the step size given in the problem, and that multiplied with this one will give you 0.1 as your k1. And if you consider k2, it will be nothing but h times f of x0 plus h comma y0 plus k1. So if you do this one, this will be 0.1 times f of x0 plus f of x0 plus h, which means at 0.1, right? X0 is 0, h is 0.1. Y0 is 1 and k1 is 0.1. Y0 is 1, so 1 plus k1 is 0.1, so this is 1.1. So if you calculate what is f of 0.1 comma 1.1 and multiply that with this, then you will be getting here 0.131. So what is y of 0.1? So we are considering h step size. Okay, so we are starting from x equal to 0 with the step size of 0.1, h is equal to 0.1. Okay, h is equal to 0.1. So my first x value will be x1, that will be equal to 0.1 because my h value is 0.1. So 0 plus h is 0.1. Okay, so we'll be getting y of 0.1 first. So which means that my x value is 0.1 now because the x value is incremented by 0.1 and the initial x value was 0. So this will be equal to y0 plus half into k1 plus k2. So this is k1 is 0.1, right? Plus k2 is 0.131 and y0, you know, y0 is 1. So if you substitute all those values, you can see from this equation. If you substitute all those values, then you'll get 1.114 5. So you will be getting y of 0.1. This is your y of 0.1. You repeat this step again one more time. So this is y of 0.1, and so that your x1 is 0.1 now, and your h value is again, which is 0.1, which is given. H is 0.1. So now you have to find out what is y of 0.2. So if you want to find out y of 0.2, then you have to add x1 plus h. Then you will get x2, and this x2 will be equal to 0.2, because now your x1 is 0.1, h is 0.1. So you'll be getting x2 equal to 0.2. This is 0.2. Then you will be getting y of 0.2, right? So then you have to repeat all this step again by taking s1 as your initial x value, and y of 0.1 as your initial y value. So in that case, if you continue this process and calculate y of 0.2, then we will be getting 1.2708. So just to take this as your initial y value for the next step, and this as your initial x value, and consider h as 0.1, do the same procedure, same steps again, and you will be getting finally y of 0.2. Instead of 0.1, you will be getting y of 0.2, and you will be getting this result. The same method you can follow in the case of fourth order Runge-Kutta method. There you have to do some more steps. That's only the difference, and it depends on the h value, and the value where you have to find out the y. Okay, uh, that will be causing the time or number of steps that you have to do in this program. For example, if you want to find out y equal to y of some 1 in this case. So if you want to find out what is y of 1, then it will be you need to do more number of steps, right? Now we'll discuss the program for this second order Runge-Kutta method, and after that we will discuss program corresponding to the fourth order Runge-Kutta method also. So first we will consider this second order Runge-Kutta method program. So as you can see in this window, this is very simple program, similar to that of Euler's method. The first line I have written, in the first line I have written the initial conditions. Okay, print enter initial conditions, which means that we have to whatever initial conditions that we have to give, that we have to provide in this part of the program. So it is just to understand what it is required, or you can just write these two instruction, that is x0 equal to float input x0, okay, and y0 equal to float input y0. So it will just take this, whatever value you have given for x0 will be taken as this x0 value. So that is the input method, as you know. So it will ask me what is this x0 equal to, okay, and what is y0 equal to. So that is obviously my initial conditions. Okay, so first we have to give x0 what the input of x0, whatever that value. Okay, and I have declared it as a float value. Okay, so we have to provide it as a float point, right, in the program. We cannot consider only integer values. We have to do for the float points, different floating points. So we have given here float, then input x0 as the string, and so that whatever you are giving value in this particular instruction will be taken as x0, and whatever you have given you are going to give value for this instruction will be taken as y0. That is my initial condition, and to show that is that as my initial condition, I'm just printing that this particular string under initial conditions. And then I have just printed here under calculation point, where we have to find out the y value. That particular point I have to give as xn. So xn will be equal to float input xn. For example, if in the previous section we discussed a problem where we had to find out the y value at point 2. So point 2 will be the x value where we had to find out the y value. So that value I had to provide here. Okay. Then I have just given this instruction to show this is the step for the number of steps calculation. Okay, so steps equal to integer input number of steps I have to provide. Number of steps which means if you are starting from x0 and if you want to find out the value at xn, and if you are considering many number of intervals in between these two. For example, if you are calculating from if you want to know the value of y at 1 and the initial point is 0, x equal to 0, and you are considering step size as h equal to 0.1, and then you will be having number of steps equal to 10. Okay, so after that 10 number of steps, you will be reaching at 1, x equal to 1. So first it will be 0, then it will be incremented by h, that is 0.1, then it will become 0.2, 0.3, 0.4, and so on. And finally, after 10 steps, you will be reaching at x equal to 1. Okay, so that is the number of steps, how many number of steps you need from the initial point to the desired x value. So that you have to provide, or you can directly give h value, that is also possible. So here I am just calculating the h value by using this step, number of steps. Okay, that's why I'm using this particular instruction. So as you can see from here, then I am defining that function, whatever function we need, dy by dx equal to something that we have to provide here. So I have used the same function that we used for calculating the value of y of 0.2 in the previous example. So I'm using that same uh, equation, x plus y square here. So I'm defining that function, and then we have to consider the second order Runge-Kutta steps. Okay, so I defined the second order. Okay, this one I have to replace it second order. Second order Runge-Kutta method RK2 here also. I'll put it as RK2. So RK2 stands for second order Runge-Kutta function. So this is nothing but the method, all the this function, whatever instruction coming under this function will be taken as the steps followed in that second order Runge-Kutta method. Okay, so don't worry about that. I'm just defining this particular function rk2 of x0 comma y0 comma xn comma n. All these parameters we have to use. So h is defined as xn minus x0 by n. N is the number of steps, I think I have given that. Yes, steps equal to, you can see here, steps equal to integer input number of steps. So I think the same thing I have to use here also. So this is x0 is the initial point, and y0, that also we have given here, x0 and y0, and xn is the final value. Okay, and here I have used these steps, right? So steps, so I have to replace, I think, this with n, right? I think there is no other, yeah, step I have to give. Okay, this one should be step. Step, that is the number of steps. So this one also will be step, so that I will be getting h value. Let me see. Okay, so then I will calculate this h value. H value is nothing but the final value, that is the value, final value of x, where we had to find out that y of y value. Okay, and that is xn. Then initial value is x0, xn minus x0, that will give the entire range divided by number of steps, that will give you h. Okay, and then print x0 slash tab, so this is for spacing, slash t, and y0 again s slash t. So it will give some space, tap space it will provide me, and then yn. Okay, so it will be like x0 space some space, y0 some space, and then yn. Okay, so that in that way it will print. And then for I in range n, for I in range n, so n is the steps. Again, it is the steps. So what is that n? This is, let me see whether we are not providing any n for steps, right? Because I'm just providing it as steps. I don't think this is okay. This I will put steps here. So for I in range steps, how many number of steps are there? That you have to consider. Then k1 will be equal to, so this is so if you are considering from 0 to 1, for example, or in the previous example we have considered for x equal to 0.2 what is the y value. So in that case we have taken h equal to 0.1. So number of steps will be 2 because initial value is 0. So first step it will become 0.1, the next step it will become 0.2. So only 2 steps are there. So in that time it will be, this steps value will be equal to 2. So for I in range 2 will come. Okay, so and then we have to go for this. So the number of steps will be 2. Number of steps will be 2. And if you consider that, then k1 will be this value, that you already know. K2 will be this, that is h into f of x0 plus h comma y0 plus k1, and from that you will be getting k equal to half k1 plus k2. It is just the half k1 plus k2 that I have given as k. Then the final solution yn will be equal to y0 plus k. So for first iteration it will take h equal to 0.1 and it will iterate that one, and then again it will go and check whether it is, the range is over or not. Then again it will calculate one more step, one more time it will continue this loop, and it will give me the result. So y0 will become yn each time. Those y0 will become yn and x0 will become x0 plus h. So each time this x will be incremented and corresponding y value will be calculated. And in the previous example, only 2 steps are there. So after 2 steps, this loop will be terminated and it will directly go to this print statement. So after this loop, it will go to this print statement and it will print the final value for this xn at this x value of y is this. Okay, that is the this line, this instruction. So at x equal to this value, that is corresponding to xn. Okay, and we are given 5 decimal places after that point, and then we have here 5 decimal places. So all these things we know, we already discussed this, those things. And then rk2, so after this we are calling that function. Okay, so here I'm just defining that function. This is my function, and at this step only I'm calling that function. Okay. Okay, so here I will be calling that function, and this, all these steps will be executed and the program will be terminated. Now if you run this program, so it will ask first the initial conditions. This print, this instruction will be displayed on this screen. You can see here under initial conditions. Then it will ask what is x0. Okay, float this input x0 that I have to provide here. So if I take the previous example, I have to provide x0 as 0. Then it will ask me what is the y0 value, initial condition for y. So that will give me, that I have to provide as 1. Then it will ask enter calculation point. At what point we have to calculate the y value. So that is 0.2. That is what we did in the example. Then the number of steps. You can provide the number of steps here, or you can change the program in such a way that you can directly put the h value. That is also possible. You don't have to calculate the h here. You can directly put h. Both way you can do that. So number of steps will be, in this case, it will be from 0 to 0.2, right? X value is changing from 0 to 0.2. So number of steps will be 2 because h I am considering as 0.1. So in first step it will become 0.1, then it will become 0.2. So that is the only. So within 2 steps, we will get y of 0.2. So 2 steps are. Then press enter. I think this is getting slow. I'll do it again. It is not connecting. Okay, so x0 is 0, y0 is 1. Calculating point is 0.2. Number of steps 2, and you can get this result. Okay, this is x0, y0, yn. That is printed because of this particular print statement. This is x0 tab, y0 tab, and yn. That is printed like this. And then we have this second printing, this print statement, and corresponding values will be printed here, x0, y0, yn, with some one tab space. Slash tab slash t. So that is here for first h value, first step, and this is for, sorry, this is for first step, and this is for second step. And the final print, this print instruction will print this particular text at x equal to 0, 0.2, we have y equal to 1.2708. That is what we have obtained in theoretical calculation. Now, if you want to change this into fourth order RK method, then you have to replace some of these portions. So I think yeah, I have provided here steps, right? So let me see whether it is working. I don't know this step. And one more step. Okay. So that you can change here. You can provide steps. We just provide the same variable here, step here, because I am providing step here. So okay, so everything is right. So I'm taking this as input, right? Number of steps equal to step. So same step I have to provide here. So I'm just doing it again, no time. So y0 is 1.2 steps. Okay, so you'll get this answer. Now, if you want to change this into fourth order RK method, then you need to consider the other values, K1, K2, K3, K4, all values you have to consider. I will just copy that program here. So only a very small change will be there in this program. Okay, so in here I will replace this with step, or you can keep it as n, no problem. Stop here, and here also I have given step. Step. Okay, now you can see I have included all those equations. Only this equation will change in the fourth order method, and k will be calculated as k1 to k2 plus 2k3 plus k4 by 6. Okay, and we have some difference in these values, k2, k3, etc. that you can see. So now if I run this program, you can see this x0 I will put 0, same example I will do, and y0 1, the enter calculation point 0.2, and the number of steps 2, Now you can see 1.273. That is very small change in the output at x equal to 0.2, y value is 1.273. I think previously it was 1.270. So there is a very small change, and this fourth order will be much more accurate to the original result. Okay, so only this part we are having the change for this fourth order RK method program from that of the second order RK method. And if you want to do this for a second order differential equation, then you have to do these steps twice, as we discussed for Euler's method. So we have to treat them simultaneously. We have to do these steps twice. So first you have to calculate for K1, and then L1 you can take for the second differentiation. Similarly, K2, L2, K3, L3, K4, L4, and so like that it will be.